Welcome to this Bruker webinar on quantifying light elements using WDS with scanning electron microscope. Thank you everyone for joining us today. I'm Laurie Pallas, Global Application Manager for the Electron Microscope Analyzers at Bruker Nanoanalytics in Berlin. I will be the host for this webinar. Our presenters are my colleagues Dr. Michael Abratis and Dr. Ralf Terborg. In this webinar, we'll review the challenges when quantifying light elements and the advantages of QUANTAX WDS solution using application examples. First, few words about our presenters. Ralf is a senior scientist in the R&D department. He studied physics at the University of Münster and TU Aachen before working at the Fritz Haber Institute in the Department of Surface Physics in Berlin. He received his PhD degree in physics from the TU Berlin in 2001. His work includes the characterization of ED spectrometers, qualitative and quantitative analysis for EDX, and development of special applications. Ralf is also a member of the ISO Microbeam Analysis Technical Committee and is also involved in projects regarding reference materials for EDX analysis. Michael studied geology at the universities of Kiel and Göttingen, where he also received his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. Michael set up and managed a microprobe lab at Jena University before joining Bruker Nanoanalytics as Senior Application Scientist for WDS in 2015. Before we start, I'll give you some housekeeping details. You should now see the outline slide on your screen. Note that this webinar is interactive, so it means that you can ask questions at any time in the according question and answer Q&A box on the right side of your screen. The presentation will last about 35-40 minutes. We will then move on to the Q&A session. If we were not able to get to your questions during this live event, we will follow up with you by email. This webinar is being recorded and will be available very soon as on-demand version. This presentation is divided in 3 parts, so Ralf will review the common challenges when analyzing light elements. Then Michael will present the QUANTAX WDS solution for SEM and present several quantification examples and the analytical conditions. So now I'll give the mic to Ralf. Thank you.
Yeah, thank you, Laurie. And hello, everybody. As we're talking about light element analysis, I would briefly like to give you an idea about the definition of the low energy range and the light elements. And on this slide, we can see EDS spectrum. I've chosen an EDS spectrum because with EDS, you can see all the lines of interest at different energies as they are recorded at the same time. This spectrum is an almandine garnet with acquired with an accelerating voltage of 20 kV. And you can see, for example, high energy lines like the IMK line at 6.4 kV, but also energy lines in the energy or low energy range. This is typically defined for energies below 1 keV. And here in this example, you can see the K line of carbon from the coating of the sample, the K line of oxygen, and the L lines of calcium, manganese, and iron. On the other hand, light elements are defined as elements with the atomic number below 11. That applies to hydrogen and helium, which is not visible in EDS or WDS, and then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Also, neon is included, but neon is normally not found in samples. If we have a look at the energies, the K-line energies of these light elements, they are all in the low energy range, below 1 keV, so that fits together. Now have a closer look at the calculated theoretical background shown in gray here. You can see that this background is clearly defined for energies above 1 keV. But for the low energy region, the background calculation is a bit more difficult. For example, the background is generally lower, and that means that we have higher errors due to statistical noise. We also have high absorption edges underneath those peaks, the low energy region, and variations of the takeoff angle detector can generally influence the low energy background shape. On the other hand, we also have a high line density, and that means that overlap is likely, especially for EDS. For WDS, the resolution is normally good enough to separate neighboring lines. And give you an idea about the theoretical background, there are some important parameters which are important for light element quantification. One is the fluorescence yield, then the quantum efficiency of the detector at a certain line or line energy, and the absorption of the line itself. And the fluorescence yield is shown here on the left-hand side versus the atomic number. And the fluorescence yield is defined for the number of photons produced divided by the number of shell ionizations. And for the K lines, this is shown in red here. For the blue line, or for the L lines, this is shown in blue. And for the M lines, this is shown in green. And we can see that for the K lines of light elements, the fluorescence yield is very low. In fact, for carbon, fluorescence yield is below 1%. So that means that less than 1% of the ionizations that are produced for light element of carbon, for example, will produce less than 1% of photons. On the right-hand side, we can see the quantum efficiency of an energy dispersive spectrometer acquired equipped with the light element window. This is the efficiency, which is defined as the number of detected X-rays divided by the number of incoming X-rays. Here also again versus energy, and we can see that it is lower for low energies than for energies above 1 keV. Another important factor is the absorption of X-rays that are generated at a certain depth and then move towards the sample surface to reach a detector. Here there is a factor called the absorption factor, and this is defined as the number of X-rays leaving the sample, so those that are not absorbed divided by the number of generated X-rays. If we have an absorption factor of 1, there is no absorption at all. But normally, especially for light elements, we have quite small absorption factors, and that means that we have significant or massive absorption. I would also like to mention that the absorption factor depends on the path length, and as the takeoff angle and the high voltage, because of the mean depth, change the path lengths, these factors also change the absorption. And to give you an idea about the absorption effect for light and heavier elements, I would like to show this as an example with calcium carbonate. Spectrum is shown here, and we can see the high energy line of calcium at 3.7 keV and peaks of 2 light elements, carbon and oxygen. And the phi rho z curves are generally needed to calculate the quantification, the concentrations, and we can see that on the next slide here. So the phi rho z curves show the ionization distribution versus the depth in the sample. And those phi rho z curves are shown here for calcium in green, carbon in blue, and oxygen in red. And the solid lines, those describe the generated radiation, and the emitted radiation is shown as a dashed line. For the calcium K, we can see that the generated and the emitted radiation are almost the same, so that means that absorption can be neglected for this high energy line. But for carbon and oxygen, we can see that there's a significant difference between the generated and the emitted radiation. And so I've shown you 3 different factors which are responsible for the line intensity, and they reduce the intensity of light elements, especially, even if we have considerable concentrations. And therefore, it's good to have a system, detection system, which is very sensitive in the low energy of light elements, and which has a good detection. And with this, I would like to hand over to Michael.
Thank you very much, Ralf, and hello, everybody. Today we focus on WDS for light element analysis. Basis of all WDS systems is Bragg diffraction. According to the Bragg equation, constructive interference of X-ray waves takes place at a specific incidence angle theta and is specific to d value of the analyzer crystal. The QUANTAX WDS is equipped with 5 to 6 analyzer crystals to cover the available energy range. A parallel beam WDS, like the present one, has an optic which captures and transforms X-rays emitted from the sample into a parallel beam that is directed to the analyzer crystal. From the analyzer crystal, a monochromatic X-ray beam is reflected towards the flow proportional counter, where the intensity of the selected wavelength is determined. There are two principal types of WDS on the market. The classical one uses a so-called Rowland circle and no optic. In such a system, the solid angle is small. That means a lot of the X-rays get lost for analysis. In contrast to that, a parallel beam WDS captures a maximum of X-rays with its optic close to the source of X-ray generation, which means the solid angle is large. And this large solid angle results in a high sensitivity for the low energy X-rays. Bruker offers several analyzers for SEM, which work together very well. QUANTAX WDS is fully integrated in the Bruker S3 analysis software. Furthermore, EDS and WDS acquire the X-rays simultaneously, and the resulting data can be combined. Therefore, you can profit from the advantages of both systems. EDS is very fast. It allows simultaneous detection of all the elements present. And it can operate also with low beam currents. WDS, on the other hand, has the advantage of providing higher spectral resolution, allowing trace element determination, and it is very sensitive for the low X-ray energies. In conclusion, WDS is ideal to complement the EDS for challenging applications such as light element analysis. Let me give you some details on the analytical conditions. Low kV is optimal for light element analysis. In the diagram on the upper left, we see an example for boron K alpha with an optimum peak intensity at 4 kV acceleration voltage. The optimum depends on the number of ionizations, which increase with an increasing excitation volume, and it depends on the absorption factor on the other hand. A larger excitation volume means an increased path length and thus a higher probability for absorption of a photon. Remember that absorption is an important factor for the light elements, as Ralf pointed out earlier. The second topic I would like to mention is about diffraction of the low energy X-rays. Analyzer crystals such as TAP, PET, or LIF can only be used for photon energies above 500 eV. For lower energies, that means longer wavelengths, diffractors with larger 2D values are required. However, this cannot be provided by any crystal structure. For this purpose, multilayer mirrors are used. These multilayers consist of two different materials with a regular, well-defined layer spacing. For the multilayer mirrors that we provide, the layer spacing is 3, 4, and 10 nanometers, or expressed as 2D value 60, 80, and 200 angstrom. Functionality of these multilayer mirrors is similar to that of diffraction crystals. Also here, the Bragg equation applies. Further details to mention are standards. For quantification, standards must be used, which can be compounds, metals, alloys, minerals, or glasses. In any case, their composition should be close to that of the sample. Analytical times can range from seconds over minutes to even hours for some mappings. The actual time depends on the required statistics, the incoming count rate, and the extent or size of the analytical task. Here we present spectra excuse me. Here we present spectra for the light elements from beryllium to fluorine, acquired on pure elements and simple compounds respectively. The spectra were recorded simultaneously with both systems, WDS and EDS. In this chart, EDS spectra are shown in orange, the WDS spectra in darker color. What is obvious is that WDS shows narrower peaks than EDS. Furthermore, we see higher peaks for WDS when we compare the vertical axis on both sides of the graph. This is especially true for the lowest X-ray energies. In conclusion, WDS shows higher sensitivity for the light elements, higher peak-to-background ratios, and better spectral resolution when compared to EDS. Now we will proceed with application examples for the light elements. We will start with beryllium, the element with atomic number 4. This slide shows an element distribution map of a carbon-coated beryllium foil on epoxy resin. Mapping of the sample could be done very fast with an acquisition time of only 1 minute for each element. Remember that WDS is energy selective, so one element is mapped after the other, first beryllium, then carbon. For each element, the suitable multilayer mirror and the respective theta angle were automatically set to determine beryllium K alpha and carbon K alpha. To demonstrate how mapping of the sample is done in practice with the Bruker software, we will see a short video now. All analytical instruments are fully integrated in the software. On the top right, you see the configurator for WDS. We start by capturing an image of the sample. After having defined the element and X-ray line of interest, we launch the mapping process. Press Acquire, and the X-ray line for beryllium K alpha is adjusted and mapping starts off. While only a single X-ray line can be measured by WDS at a time, multiple elements are acquired simultaneously by EDS. When time is up for mapping of the first X-ray energy, the second energy is set up by changing the multilayer if required and adjusting the correct theta angle. Now, carbon K alpha is mapped by WDS, while EDS is continuously adding more counts to the present mapped spectrum. Finally, combined WDS-EDS mapping is finished according to the predefined acquisition time of 1 minute for each of the two elements. The second video shows a qualitative spot analysis by WDS. We are still on the same sample. First, we choose a tool for the object to be analyzed, then we set a spot in the image and start the acquisition. Immediately, we see the EDS spectrum, and the WDS is adjusted for the defined starting energy. A suitable multilayer is inserted and turned to match the appropriate theta angle. Since WDS is energy selective, a spectrum can only be recorded sequentially, while the spectrometer is continuously adjusting the angle of the multilayer. The scan across the beryllium K alpha peak is completed step by step, and the X-ray energies in the WDS display are steadily changing. Now we can use the S-Prefinder function to identify or confirm the detected peak. The qualitative spot analysis is finished. We recorded a so-called energy range scan. In this slide, we present WDS range scans for beryllium on 4 different silicate minerals. 2 of them contain beryllium, namely 7% in the mineral beryl and 2% in the mineral tuctopite. The other 2 minerals, albite and olivine, do not contain any beryllium. All 4 minerals are silicates, so they all show a peak for silicon L. And the actual challenge for X-ray analysis is to resolve beryllium K from silicon L as a prerequisite for beryllium determination. This resolution cannot be done by EDS, but only by WDS. We will proceed with applications on boron, element with atomic number 5. The first application example is determination of boron contents in glasses, so-called borosilicate glasses. An EDS spectrum of such a glass is shown on the right side. The WDS range scan on 3 different glasses proves the scans prove that boron can be determined even in low concentrations of 0.2 weight% or lower. The analysis were done at low kV and in low vacuum mode to avoid any coating and charging of the sample during analysis. Low vacuum is no problem for the QUANTAX WDS. The second application example for boron shows a set of layered samples. The profile on the lower left indicates that the samples have a boron carbide layer placed on silicon substrate and covered with a thin quartz glass layer. Thicknesses of the boron carbide layers range from 1 nanometer to 50 nanometer. The diagram in the center of the image presents the range scans for boron and proves that boron can actually be determined down to the thinnest layer. To the right, we see two graphs comparing the capability of two different multilayers covering the energy range of interest. The 200 angstrom multilayer in the upper graph shows higher count rates, but can indicate the boron peak only up to the 10 nanometer thin layer. On the other hand, the 80 angstrom multilayer lower graph indicates the boron peak even for the thinnest layer of only 1 nanometer, though with lower count rates. This comparison points out to the fact that the peak to background ratio is actually more important for the limit of detection than the count rate. A third example for boron presents mapping of low boron contents in a steel. The combined WDS-EDS mapping indicates that the steel contains phases called cementite, which are characterized by enrichment of carbon, manganese, and boron. Boron contents determined by WDS are 0.4 weight% in these phases as compared to 0.2% in the steel matrix. Note that the cementite inclusions are less than a micron in diameter. Now we will present some application examples for carbon, element with atomic number 6. Here we see mappings for carbon acquired by WDS on two different steels. Both maps were recorded within only 5 minutes. The image to the left shows a carbon-rich steel with more than 1% average carbon content, and the carbon is concentrated here in chromium carbide phases with about 6% carbon, shown in green. In the other steel, carbon contents are about 10 times lower. Nevertheless, two phases, martensite and ferrite, could well be distinguished based on their carbon contents because of the large concentration difference. Fast mapping was possible here for both samples, and it is also highly recommended because of the contamination issue during analysis. We can already see carbon deposition in the image on the right at the margins of the mapped area. Carbon contamination is a problem during analysis in an SEM. Hydrocarbons are ubiquitous in the SEM chamber. They are derived from the pumps, from the sample, or simply from the air introduced during venting. These hydrocarbons are cracked within the electron beam, and carbon is instantaneously deposited on the area of analysis. See the SE image on the left. The amount of carbon deposited on the sample surface increases over time, as shown with the WDS range scan to the right. Carbon contamination is also affecting carbon quantification. Detection limits for carbon are relatively high due to contamination, but not related to the WDS performance. When we analyzed carbon contents in certified steel, in several samples of certified steels, without dedicated cleaning of the SEM, detection limits were at 0.4 weight%. See the graph on the left side. After several cycles of plasma cleaning, we could lower the detection limit by a factor of 2. Further lowering of the limit of detection is possible by the implementation of technical measures, such as an air jet to blow away the hydrocarbons from the spot of analysis and a cooling finger to capture them. Now we will have a look on samples with nitrogen, light element with atomic number 7. First example for nitrogen is mapping of a rock full of nitrates. This rock, so-called caliche ore, is from the Atacama Desert in northern Chile and contains sodium nitrate, potassium nitrate, and sodium chloride, besides accessory phases, accessory minerals, which are sulfates mostly. Nitrogen, the sodium nitrate, contains the most nitrogen, 16.5%, and is shown in dark red. Niter, the potassium nitrate, contains less nitrogen, 13.9%, and is shown in pale red. Halite, the sodium chloride, contains no nitrogen at all. It is presented in green. The respective intensities for nitrogen K alpha are also shown in the range scans to the right of the map. WDS and EDS mapping is simultaneous. Therefore, now we can compare the results of both detection systems. The map for nitrogen K alpha recorded by WDS is presented on the left. The map recorded by EDS is presented on the right. There is not much difference between the two maps. We conclude for major elements, WDS is not a real gain for the analysis. However, for the resolution of peak overlaps and for the determination of very low element contents, trace elements, it is of great help. To stress this point, we see here an application of nitrogen quantification in certified steel samples. The diagram of measured versus accepted values for nitrogen indicates that contents as low as 100 ppm can well be determined by WDS. EDS instead has a detection limit that is an order of magnitude higher. Last element for today is oxygen, atomic number 8. Here we see EDS spectra and WDS range scans for cast iron on the left and stainless steel on the right. Both samples contain about the same amount of oxygen. In the cast iron on the left side, both WDS and EDS can detect oxygen. Note the hump at 0.525 keV that appears also in the EDS spectrum. In the steel, however, only WDS can resolve the minor oxygen peak between the two chromium L lines. For EDS, this peak is too small and hidden in the overlap. With this, I would like to conclude. The QUANTAX WDS is designed with a focus on low X-ray energies, including the light elements which we presented today. With its parallel beam optic capturing X-rays close to the source of origin, the QUANTAX WDS has a high solid angle. In consequence, the QUANTAX WDS is very sensitive for the low energy X-rays. It can well analyze the light elements with low kV, low beam currents, and in low vacuum. Due to its higher peak-to-background ratio and higher spectral resolution, the WDS is an ideal complement to EDS. Thank you very much. And I hand over.
Thank you, Michael. Thank you, Ralph and Michel, for this very interesting presentation. We will now have our Q&A session. So please, if you have a question, submit it in the Q&A box and on the right side of your screen and click on Submit or Send button. So please go ahead if you have a question. Meanwhile, we have received a few questions. So I will get started by asking the first question from the audience. One for Ralph. Why is absorption so important for low energies or light elements?
Yes, as I pointed out, absorption can often be neglected for high energy lines, as we have seen in the case of calcium in the calcium carbonate sample. But for the low energy lines, this absorption has a significant effect, and without doing the absorption correction, the concentrations will be underestimated by a significant amount, because the light elements, the absorption factor can be sometimes around 0.1, which means that the line intensity of such a low low energy line can be reduced by a factor of 10 or so. So in that case, absorption is extremely important to be able to calculate the correct concentrations for such light elements.
Thank you, Ralph. Next question for Michael. I learned that sample preparation is important for WDS, but you showed rough and uncoated samples. Can you comment on that?
Oh yeah, that's a good question. Yeah, I didn't say much on sample preparation so far. So it depends actually on your analytical task. If you do qualitative analysis only, then preparation is not a great issue. So like you have seen, we can also map a rough surface like the rock with the nitrates. So it was quite rough. You will see some differences in the intensities, but it could be sufficient for a qualitative map. But for quantification, for a quantitative map or quantitative point analysis, good sample preparation is very important. So you have to polish your sample very well, and you have to make it conductive so that there's no charging. So this is all required because you are comparing with standards, and you have to make sure that you have the same conditions, that you don't reduce the count rates by rough surface, so with a lot stray photons. So for quantification, sample preparation is very important.
Thank
So
you, Michael.
this is to add this is the same for EDS also when you do standard-based quantification with EDS. So it doesn't not depend on the technique EDS or WDS, but it depends on the method of quantification. For standardless quantification, what is possible with EDS but not with WDS, you can also quantify a rough surface. But for standard-based quantification, either EDS or WDS, you need well-polished sample surfaces.
Thank you, Michael. Another question for you. Did you observe peak shifts when analyzing light elements?
Oh yeah, that's a point I left out here because I thought it might be too much, but actually I observed it, and I could show some more slides on that, or at least one. So peak shifts are a great issue for the light elements, or they're commonly observed, and we could see that, for example, with boron in the left diagram and with beryllium in the right diagram. So we observe peak shifts by several electron volts, like 4 or 3 or 4 electron volts, and this is well known. That peak shifts occur for the light elements. It cannot be observed for heavier elements, but for light elements, binding affects obviously the atomic structures. So as you know, the characteristic X-rays, they depend on the transition of the elements, in this case from the L position, the L shells to the K shells, and the spacing of the orbitals or the shells in the atomic model determines the energy of the characteristic peak, and when the distance of this shell is changing, the energy changes also, and the chemical binding has some influence on the atomic structure. And at least for the light elements, it can be observed, like here for boron and beryllium. And the effect is very minor for heavier elements, but here it can be seen, and it can also be used to identify chemical compositions. Yeah.
Thank you, Michael. Maybe a question for Ralph. What is causing the I'm not sure I've already asked this one. No. Okay, I was not sure. Sorry. Going through all the questions. What is causing the drop in the detector efficiency for low energies? Thank you.
Yeah, I've shown the detector efficiency versus the energy in one of the slides, and the efficiency was calculated for a detector with a light element window, and the light element window also contains certain layers, and windows are used normally to protect the detector. And the efficiency is defined as the number of detected X-rays divided by the number of incoming X-rays, and all incoming X-rays make it to the detector crystal to get detected. Some of the photons can get absorbed in the window or in the contact layer of the detector, for example. And this is especially true for low energy lines. Therefore, we have quite massive absorption effects in the window or in the contact layer of the detector, and that will reduce the efficiency. If you like to analyze light elements with an EDS, for example, you can also use a windowless detector, which has an enhanced detector efficiency.
Thank you, Ralph. Another question for Michael. What is the spatial resolution for WDS?
Spatial resolution. Yeah, so far I talked about spectral resolution mostly, but spatial resolution in principle it's the same like with EDS when we apply the same conditions, so the same acceleration voltage and the same beam current. We are registering the same signal, the X-rays, from the same volume, so the resolution is the same in that case. But EDS can also work with lower beam currents than WDS. In that case, with a lower beam current, we are focusing on a smaller spot, and that could help to reduce the lateral resolution, the spatial resolution. But with the same conditions, we get the same spatial resolution. There is a further question here. So concerning resolution of phosphorus K alpha and zircon L lines, so which are about 30 electron volts apart, and this is something that WDS can resolve, but EDS cannot. So there's an overlap for EDS, but WDS can resolve such a difference in energy. Yeah. So.
Thank you. So thanks again for this very interesting presentation. We have now run out of time and conclude our Q&A session for this webinar. As a reminder, today's event has been recorded and will be available for viewing very soon as on demand on our website. Thank you for being with us today, and we hope to have you again at future webinars. Goodbye.